in oil operations. This isn't just cool tech, it's chemistry, engineering, and real-world impact, all in one. Let's dive into the science behind this breakthrough. If you enjoyed this video and want to see more science breakthroughs, don't forget to subscribe to the For Science Sala Lotfi channel.
Welcome to For Science Sala Lotfi channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous. Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Sala Lotfi Channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Hey everyone, welcome back to the channel. Today I'm diving into a breakthrough that could change how we handle one of the messiest byproducts of oil extraction, petroleum-produced water. Now, you might not think about it, but every time oil is pulled out of the ground, a ton of water comes up with it. And it's not just any water, it's packed with oil droplets and all sorts of gunk. If we just dumped this stuff back into the environment, it'd be a disaster. But here's the catch. Even our best treatment systems struggle to get every last bit of oil out, especially at those super low concentrations where it really matters. That's where a fascinating study published in the journal Separation and Purification Technology steps in. A team of researchers from Egypt and Saudi Arabia thought, what if we stopped relying on just one method and got clever with combining technologies? So first up, they engineered this wild new porous resin composite. Imagine a sponge, but on a molecular scale, designed specifically to snatch oil out of water. This isn't your kitchen scrubber. It's crafted with precision, so it actively attracts and holds on to tiny oil droplets at the oil-water boundary. Once the resin's done its job, the scientists take the water and run it through microfiltration. But here's the trick. Instead of using filters as the main workhorse, they use them as a final polish, sweeping up any stubborn leftovers. This two-step combo? It gets the water so clean it's basically oil-free. That's a huge leap beyond what single-step methods can do. The brains behind this? Professor Dr. Hussein Ibrahim Abdel Shafi, Water Research and Pollution Control Department, National Research Center, Doki, Cairo, Egypt. Associate Professor Dr. Mona Mansour, Analysis and Evaluation Department, Egyptian Petroleum Research Institute, Omar Street, Nasser City, Cairo, Egypt. Associate Professor Dr. Mohammed Mohammed Touni, King Khaled Univ, Tohama Branch, Chemistry Dept, Saudi Arabia and Egyptian Atomic Energy Authority, Egypt. They're not just experts in water treatment and environmental science. They're also pushing the boundaries with radiation chemistry and advanced material design. What I love about this is how it shows real teamwork between science fields. Materials science for building the resin, radiation tech for boosting its performance, and classic engineering for putting it all together. It's a perfect example of how smart thinking and collaboration can solve gritty, real-world problems. In the next episode, I'll break down how they actually made this resin, why they used irradiation, and what these results mean for recycling water in the oil industry. Stay tuned, because science isn't just about ideas, it's about action and impact. This is For Science Sala Lotfi channel, where research meets reality. See you soon.
Before I get into oil, reactors, or cutting-edge materials, let's talk about something way less glamorous, water. But not the kind you pour into a glass or swim in on a sunny day. I'm talking about the murky, contaminated water that flows out of oil wells every single day, mixed up with crude oil, heavy metals, salts, and all sorts of stubborn organic pollutants. This stuff is called petroleum-produced water, and honestly, it's a big deal. Here's a number for you. For every barrel of oil pulled out of the ground, almost 3 barrels of this nasty water come up with it. And in aging oil fields, the ratio doesn't just creep up. It explodes. Sometimes it's 10 to 1, or even more. So the real issue isn't just, how do we get more oil out of the ground? It's, what on earth do we do with all this dirty water? For decades, the answer was depressingly simple. You just treat it, barely enough to make it safe for disposal, then pump it underground or dump it into evaporation ponds. Out of sight, out of mind, right? But that approach is running on borrowed time. Water scarcity is biting harder, environmental regulations are stricter, and the cost of just getting rid of it keeps going up. Disposing of this stuff isn't just a technical hassle, it's an environmental and economic headache. So, here's the twist. Scientists, engineers, and even oil companies are starting to ask a radical question. What if this so-called waste could actually become a resource? I'm talking about transforming one of the world's most problematic industrial waste streams into, well, something useful. Maybe irrigation water, maybe brine for industrial processes, or even, if we get really ambitious, reclaimed water that's safe for people and nature. This isn't science fiction, it's an emerging scientific revolution. In this episode, I'm diving into the science, the engineering, and the big ideas that are turning the oilfield water problem on its head. We'll explore how advanced filtration, clever chemistry, and even biology are being pushed to the limits to clean up this water. Because if we can solve the oilfield water problem, we're not just making the oil industry cleaner, we're rewriting the story of industrial waste. From waste to resource. That's the revolution. If you found this fascinating, don't forget to subscribe to the For Science Sala Lotfi channel for more deep dives into science and innovation. When oil and gas are extracted, we also get produced water. A complex chemical-laden mix that's far more than just oily water. It's a cocktail of oil droplets, dissolved oil, extreme salt, solids like sand and rock, and a host of added and natural chemicals. Some oil floats as visible droplets, but much of it is dissolved or dispersed so finely you can't see it. The salt content? Often many times higher than seawater, making it a super salty brine. Add in suspended solids, drilling chemicals, and dissolved organics, and you've got a real treatment challenge. Each component, oil, salt, solids, chemicals, needs a different removal strategy. You can't just use one trick to clean it all up. It's like trying to unscramble an egg. Once mixed, separating everything is incredibly tough. That's why produced water is such a big scientific challenge. Understanding what's inside is the first step to solving the problem. The old ways of cleaning just aren't enough for today's complex mix. We need new solutions for a new level of complexity. Let's see why. The main culprits in produced water are tiny oil droplets, dissolved chemicals, extreme salt, and suspended solids. Free oil is easy to remove, but microscopic droplets and dissolved oil form stubborn emulsions. Think mayonnaise that won't separate. Dissolved organics are invisible but dangerous, raising chemical oxygen demand and threatening aquatic life if released. High salt content makes the water corrosive, damaging equipment and making disposal or reuse difficult. Removing this much salt is far harder than desalinating seawater. Suspended solids cloud the water and clog equipment, while also trapping oil and chemicals. Each of these troublemakers needs a different removal method. The water may look clean, but hidden pollutants remain. That's why produced water is so tough to treat. It's not just what you see, it's what you can't see that causes the biggest problems. Traditional methods can't handle all these invisible threats. We need smarter, multi-step solutions. Let's look at what's been tried so far. For decades, gravity separation was the go-to method. Let oil float to the top, skim it off, and filter out big solids. It's simple and works for large oil droplets and visible particles. But gravity can't remove tiny emulsified oil or dissolved chemicals. Salt and most organics pass right through, leaving the water still polluted. These methods are like raking leaves. You get the big stuff, but the small debris stays behind. The water may look clearer, but invisible contaminants remain. So while gravity and basic filtration are a good start, they're nowhere near enough. The real threats, microscopic oil, dissolved chemicals, and salt, are left untouched. We need more advanced solutions to truly clean produced water. Let's see what happens when clean enough isn't good enough. Often, treated produced water is re-injected underground to help extract more oil. But if the water isn't truly clean, it clogs the tiny pores in the rock, blocking oil flow. Microscopic oil, solids, and chemicals plug up the reservoir, reducing oil recovery and raising costs. It's like pouring coffee through a clogged filter. Nothing moves. The result? Less oil, more problems, and expensive fixes. Treating only what's visible leads to hidden damage underground. Out of sight isn't out of mind when oil production drops. The lesson? Clean enough water just isn't good enough for reinjection. We need to do better. No single method can clean produced water completely. The solution? Combine multiple technologies in a treatment train. Start with gravity separation for big oil droplets. Use flotation to lift smaller droplets, then filters to catch solids. Advanced oxidation breaks down dissolved chemicals. Reverse osmosis removes the stubborn salt. Each step targets a specific contaminant, making the water cleaner at every stage. This integrated approach is the future, smarter, more effective, and sustainable. With teamwork between technologies, we can turn waste into a valuable resource. That's the power of science in action. If you enjoyed this video, don't forget to subscribe to For Science Sala Lotfi channel for more fascinating science content. Join our community and stay updated with the latest discoveries.
Oil spills are a huge environmental disaster, and cleaning them up is tough. But now, scientists have a breakthrough, a two-step process for separating oil from water. Imagine cleaning a dirty dish. First you scrape off the big mess, then you scrub away the rest. This new method works the same way. Step 1 uses a special resin to grab most of the oil from the water. Step 2 uses microfiltration to remove the last tiny droplets. By combining these two techniques, the process is much more effective than using either alone. The resin does the heavy lifting, while the filter polishes off the job. Each part does what it does best, making cleanup faster and cleaner. It's a smart, efficient solution to a messy problem. That's how teamwork in science leads to cleaner water. So, what's this special resin? Think of it as a custom-made sponge that loves oil and hates water. Scientists used radiation grafting to add oil-attracting groups to a polymer, making it super oleophilic and hydrophobic. When placed in oily water, it acts like a magnet, pulling oil away from the water's surface. The resin's porous structure traps oil fast, removing over 90% in no time. It's engineered to work right at the oil-water interface, where it matters most. Unlike old materials, it stays solid and is easy to collect after use. This is material science in action, a targeted, efficient oil remover. It's the game changer that makes the whole process possible. Traditional oil cleanup methods use adsorbents like activated carbon or clay, but these soak up water too, making them heavy and inefficient. They often break down into sludge, creating more mess. In real-world spills, they get saturated quickly and lose effectiveness. The new resin is different. It's tough, stable, and targets oil at the surface. Its special chemistry attracts oil molecules, while its structure offers a huge surface area. This means faster, more selective oil removal. Instead of just being a sponge, it's engineered for the job. It's a leap from old, passive materials to a smart, active solution. That's what sets this breakthrough apart. After the resin removes most of the oil, microfiltration steps in. This membrane filter catches the last tiny oil droplets, letting only clean water through. Used alone, microfilters clog fast. But here, they just polish the water. The resin does the heavy work, so the filter lasts longer and works better. This two-step system is efficient, sustainable, and cost-effective.
The remarkable performance of this resin is no accident. Every aspect of its design, from the molecular level up to its visible structure, is carefully engineered to achieve maximum efficiency in separating oil from water. Scientists spend years perfecting the synthesis process, ensuring that the resin's internal architecture is optimized for its intended purpose. At the heart of its effectiveness lies a unique feature: multi-scale porosity. This means the resin isn't just a solid block, but a labyrinth of pores of different sizes, all working together to enhance its capabilities. The material contains macropores, which are large enough to allow fluids to flow through easily, micropores that provide additional surface area, and nanopores that interact with molecules at the smallest scale. These pores are interconnected, forming a continuous network that allows oil and water to move freely within the resin. This intricate structure results in an enormous specific surface area, over 400 square meters per gram. That's more surface area in a single gram than a tennis court, providing countless sites for oil molecules to attach and be captured. But the resin's true intelligence is revealed at the oil-water interface. This is where the challenge of separation is greatest, and where the resin's design shines. Its surface is engineered with hydrophobic regions that actively attract and bind oil molecules, drawing them out of the mixture with remarkable selectivity. Meanwhile, hydrophilic regions ensure the resin remains anchored in the water phase, preventing it from floating away or becoming saturated with oil too quickly. This dual nature allows the resin to position itself precisely at the thin, unstable boundary between oil and water, exactly where oil removal is most effective. It's a dynamic process, with the resin constantly adjusting to maximize contact with the oil layer. Thanks to this sophisticated design, even the thinnest oil films, sometimes invisible to the naked eye, can be efficiently captured and removed, making the resin an invaluable tool for environmental cleanup and industrial applications alike. I invite you to subscribe to the For Science Sala Lotfi channel to follow more outstanding scientific content.
Tough jobs, like cleaning up oil spills. Scientists build these materials from the ground up, giving them special features for specific challenges. Imagine building with Legos. You can make a simple wall or a complex spaceship with hidden compartments. Advanced resins are like that spaceship, intricately designed for a purpose. Their secret? A complex internal structure, invisible to the eye, that delivers big results. The magic comes from two things: porosity, how many holes the material has, and the interface, where oil and water meet. Combine a superporous structure with chemistry that works at the oil-water boundary, and you get a high-tech tool, not just a sponge. The resin's performance is all about controlling its internal architecture and chemical personality. Let's dive in and see how these resins are built for maximum effectiveness. We'll explore how different pore sizes work together, and how the chemistry lets the resin sit perfectly between oil and water. By the end, you'll see it's not magic. It's science and engineering making our world cleaner. Science is the real secret sauce. Porosity isn't just about holes, it's about a smart network of pores in all sizes. Picture a highway system inside each resin bead. Macropores are the superhighways, letting oil and water flow quickly inside. Without them, everything would clog at the surface. Once inside, the liquid moves onto smaller roads, micropores, spreading out and slowing down for better interaction. Then come the nanopores, the tiniest passages, creating a vast surface area. This multi-scale network, from macro to micro to nano, pulls liquids in fast and spreads them out deep. Unlike a kitchen sponge, these pores are all connected, ensuring every bit of resin is used. The result? Rapid uptake and thorough contact. Perfect for high-performance cleanup. It's a masterpiece of tiny engineering. Every pore size plays a role, working together for maximum efficiency. That's what sets these resins apart. All this happens on a microscopic scale. Why are those tiny nanopores so important? It's all about surface area. A resin bead may look small, but inside, its surface area is enormous. Hundreds or thousands of square meters in just a few grams. This vast internal landscape is where the real action happens. More surface area means more sites for oil to stick, making cleanup much more effective. Think of slicing bread. More slices mean more surface to toast. The resin's pores do the same for oil and water. It's not just about soaking up liquid, it's about maximizing contact. The interconnected pores ensure this huge surface is accessible, not hidden away. Macropores let liquids in, while micro and nanopores provide the playground for cleanup. So, a tiny bead is actually a world of surface area, ready to work. That's the power of smart porosity. It's the secret to the resin's strength. Structure is only half the story. The resin's chemistry is just as important. These resins are amphiphilic, part hydrophobic, oil-loving, part hydrophilic, water-loving. This dual nature is key for cleaning up oil spills. Oil and water don't mix, but the resin bridges the gap. At the oil-water interface, hydrophobic parts grab oil, while hydrophilic parts anchor the resin in water. The resin positions itself perfectly at the boundary, never floating away or sinking. This self-positioning is a game changer. It means the resin is always in the right spot to capture oil. Hydrophobic regions pull in oil. Hydrophilic regions keep the resin stable in water. Combined with massive surface area, this chemistry makes the resin a powerful oil-capturing machine. It's not just a sponge, it's a smart material. The resin knows exactly where to go and what to do. That's the brilliance of its design. Let's put it all together. The resin's vast surface area and dual chemistry let it target even the thinnest oil films on water. The beads migrate to the oil-water interface, hydrophobic parts grabbing oil, hydrophilic parts anchoring in water. Each bead captures a surprising amount of oil, thanks to its nanopores. The resin doesn't just absorb thick spills, it wipes the surface clean, even removing thin sheens. It's like a supercloth for oil, leaving water much cleaner. This efficiency is no accident, it's the result of brilliant design. The interconnected pores and amphiphilic chemistry make the resin a powerful cleanup tool. Science and engineering in action, tackling real-world challenges. That's the secret of super resins. If you enjoyed this video, don't forget to subscribe to the For Science Sala Lotfi channel for more fascinating science stories.
Science isn't just about forming theories or making predictions. It's about putting those ideas to the test and seeing what the data actually reveals. Every experiment tells a story, and the numbers are the real proof of progress. In the world of water purification, results are everything. We need to know not just if a process works, but how well it works, and what the data can teach us for future improvements. So, what does the data say about solid phase extraction? In a real-world test, scientists started with water heavily contaminated, almost 150 grams of oil per liter. That's a thick, murky mixture, far from anything you'd want to drink or release into the environment. The challenge: could a cartridge packed with just 10 grams of specialized resin make a difference? The sample was carefully poured through the cartridge, and the results were measured with precision. After just one pass through the resin, the oil content plummeted to only 1.13 grams per liter. That's a dramatic reduction. Over 99% of the oil was removed in a single step. The transformation was visible. What started as a cloudy, oily mess became a much clearer liquid, showing the power of this extraction method. But the story doesn't end there. Other important water quality indicators were also measured. Conductivity dropped, meaning fewer dissolved ions. Turbidity, which measures how cloudy the water is, improved significantly. Chemical oxygen demand, a key indicator of organic pollution, also decreased, showing that the water was not just less oily, but cleaner overall. However, even with these impressive results, the water wasn't completely oil-free. If you looked closely, you could still spot traces of oil, tiny droplets, or a faint sheen on the surface. This highlights a crucial point. Even the best single-stage process has its limits. That's why a second purification stage is essential. By adding another layer of treatment, we can push the water quality even further, aiming for truly clean, safe water that meets the highest standards.
Today, let's talk about clean water and how we get it using microfiltration. Imagine a spaghetti strainer, but way finer. So fine it can trap things you can't even see. Microfiltration uses membranes with microscopic pores, much smaller than a human hair. Water passes through, but bacteria, sediment, and other particles get trapped. It's a physical barrier, not a chemical process, just pure physics at work. This method is used in water treatment plants to remove contaminants and make water safer. By filtering out the bad stuff without chemicals, it's better for our health and the environment. The result? Water that's much cleaner and clearer. Microfiltration is a powerful tool for ensuring access to safe water. Science at its best, helping us solve big problems, one drop at a time. If you enjoyed learning about microfiltration and want more science content, don't forget to subscribe to the For Science Sala Lotfi channel. Hit that subscribe button now and join the For Science Sala Lotfi channel for more fascinating science videos. Scientists have found a smarter way to use microfiltration as the final polishing step in water treatment. Before reaching the membrane, water goes through other processes like coagulation and settling, removing most large particles. By the time it gets to microfiltration, the water is already pretty clean. Now, microfiltration focuses on catching the tiniest remaining particles. This new sequence lets each treatment stage do what it does best. Microfiltration at the end delivers a precise finishing touch. The result is a more efficient, logical, and effective water treatment system. It's all about using the right tool at the right time. That's smart engineering in action. Filters can get clogged, a problem called fouling. In traditional setups, microfiltration faces lots of gunk and needs frequent cleaning, but with the new polishing approach, water is much cleaner before it hits the membrane. Fewer particles mean less fouling and longer times between cleanings. This keeps the system running smoothly and saves energy. Membranes last longer and need fewer harsh chemicals for cleaning. Operational costs drop, and the process becomes more sustainable. Simply changing the order of treatment makes a huge difference. It's a win for efficiency and the environment. That's the power of smart process design. So, what does this final microfiltration step target? The tiniest troublemakers, microscopic oil droplets and fine particles. Industrial wastewater often contains tiny oil droplets that are tough to remove. Microfiltration membranes physically block these droplets and any lingering particles. If a contaminant is bigger than the pore, it's stopped, simple as that. This makes microfiltration extremely reliable for removing what's left after other treatments. The result is water that's clear, free of oil, and ready for reuse or safe discharge. It's a specialized tool for a specialized job. The clarity and purity achieved are hard to match with other methods. Microfiltration delivers that final, crucial clean. The results of this final polishing step are impressive. Microfiltration removes nearly all oil droplets, making water oil-free. Turbidity drops to extremely low levels. Water looks crystal clear. This clarity means safer water, since particles can harbor harmful microbes. The process also lowers chemical oxygen demand, reducing environmental impact. We're not just meeting minimum standards, we're making water truly clean, oil-free, clear, and with a lower chemical footprint. This water is ready for any use. It's a testament to innovative science protecting our most precious resource. Clean water isn't magic, it's smart engineering.
Cleaning up pollution is tough, but scientists have a powerful new tool, radiation chemistry. Using controlled energy like electron beams, we trigger chemical reactions that break down pollutants at the molecular level. High-energy electrons split water molecules, creating reactive particles that destroy harmful chemicals. This technology is revolutionizing environmental engineering, making cleanup more effective and affordable. It's science in action, helping us clean up legacy pollution and protect water sources. By integrating radiation chemistry, we're building a more sustainable future for our planet. If you enjoyed learning about these innovations, don't forget to subscribe to the For Science Sala Lotfi channel for more fascinating science updates. One of the best things about this technology? It's scalable. We can build small systems for factories or massive ones for cities, thanks to adjustable electron beam accelerators. This flexibility lets engineers customize solutions for specific problems, unlike many traditional methods. In oil recovery, radiation chemistry transforms water, creating nanomaterials that help extract more oil efficiently. It's like giving water a superpower, boosting output without harsh chemicals. Older methods can damage underground rock and harm the environment, but radiation-based treatment is gentler and safer. It modifies water without adding corrosive substances, protecting both equipment and the well's structure. The result? Longer-lasting wells, less environmental impact, and smarter resource management. Engineers can fine-tune treatments for different pollutants or optimize resource extraction. This precision opens new possibilities for tackling tough industrial and environmental challenges. It's a true engineering breakthrough. For technology to succeed, it must make economic sense. And radiation chemistry does. In industries like oil recovery, it lets companies treat and reuse water, slashing the need for fresh supplies and saving money. Cleaning water on site means less costly disposal and fewer environmental risks. By treating wastewater at the source, companies cut operational expenses and protect local resources. The process also extends the life of wells and equipment, since it avoids harsh chemicals that cause wear and tear. Lower maintenance and fewer replacements mean big savings over time. Plus, this technology enables on-site production of advanced materials, like nanomaterials, reducing the need for imports. That can spark local manufacturing and create new jobs in technology and industry. It's a win for the environment, the economy, and local communities. Saving water, cutting costs, and building resilience. These impacts are impressive. Radiation chemistry isn't just smart science, it's smart business. It's a sustainable way forward. A breakthrough in the lab only matters if it works in the real world, and radiation chemistry is proving itself. Companies are now using this technology to treat industrial wastewater and clean water used in energy production. These robust automated systems are built for the massive scale of factories and oil fields. The technology is helping industries save money, reduce pollution, and protect resources. Advanced technology can support both the economy and the environment. They don't have to be in conflict. That's the promise of radiation chemistry in action.
This research tells a larger story, one that goes far beyond the walls of the laboratory. It's about the innovative minds who are constantly searching for ways to address some of the world's most pressing environmental challenges. Every day, scientists and engineers collaborate, brainstorm, and experiment, driven by a shared goal, to transform what we once considered waste into valuable resources that can benefit society. The convergence of materials science, radiation technology, and environmental engineering is at the heart of this transformation. By combining their expertise, these professionals are able to develop new methods and technologies that not only neutralize hazardous materials, but also recover useful components from them. This multidisciplinary approach is essential for tackling complex industrial problems that affect both our environment and our health. Turning hazardous waste into a usable resource might sound like something out of science fiction, but it's happening right now. Across the globe, facilities are using advanced processes to convert dangerous byproducts into safe, reusable materials. These efforts reduce pollution, conserve natural resources, and create new economic opportunities. This is applied science in action, meticulously planned, rigorously tested, and always guided by a sense of responsibility. Every step, from initial research to real-world application, is carried out with care and critical thinking to ensure safety and effectiveness. At the For Science Sala Lotfi channel, we are passionate about showcasing this kind of groundbreaking research. We believe it's important to highlight the people and the processes behind scientific innovation, making complex topics accessible and engaging for everyone. Here, science isn't just explained, it's brought to life, showing how discoveries in the lab can have a real positive impact on our world. Join us as we explore the fascinating journey from waste to resource, and see how science is truly connected to reality. If you enjoyed this video and want to see more inspiring science stories, don't forget to subscribe to the For Science Sala Lotfi channel. Hit the subscribe button and join our community as we uncover more ways science is changing the world.
I'm sure you've heard the news. Groundbreaking research is changing the way we think about petroleum science. Let's celebrate the scientists making it happen. Here's why their work matters. A heartfelt thank you to Professor Dr. Hussein Ibrahim Abdul Shafi, Associate Professor Dr. Mona Mansour, and Associate Professor Dr. Mohammed Moharm El Tuni. Their dedication and expertise have led to a well-designed practical study that tackles real environmental and industrial challenges in the petroleum sector. This is the kind of applied research that transforms big problems into real-world solutions. I'm Professor Dr. Salah Lotfi from the Egyptian Atomic Energy Authority, and it's been an honor sharing this journey with you on For Science Salah Lotfi channel. Thank you to each and every one of our viewers. Your passion for science keeps this conversation alive. Drop your thoughts and scientific comments below. Your voice enriches our community. Thanks for watching and for supporting science that truly makes a difference.